For decades, astronomers have depended on space-based observatories such as Hubble, James Webb, and Chandra to study the universe without the interference of Earth's atmosphere. But a new observatory on the ground is changing that picture in a remarkable way. High on a mountain in Chile, the Vera C. Rubin Observatory has begun looking across the southern sky with an enormous digital camera designed to survey the cosmos on an entirely different scale. Its images cover huge areas of the sky while revealing incredibly fine details, producing an enormous stream of information that astronomers will be studying for years. At the center of this extraordinary system is a camera containing billions of pixels. A single exposure can cover an area of sky equivalent to dozens of full moons, while simultaneously revealing distant galaxies, stars, nebulae, asteroids, and countless other objects. Even the earliest observations have demonstrated what this observatory is capable of. Galaxies caught interacting with one another, stellar nurseries, ancient clusters, and previously unknown asteroids appeared in the data almost immediately. The real importance of Rubin, however, is not simply the beauty of its photographs. The observatory was designed to repeatedly photograph the same regions of the sky, allowing scientists to detect changes as they happen. Exploding stars, moving asteroids, variable stars, and unexpected objects can therefore be identified much faster than ever before. The story of this telescope began more than 2 decades before its first public images. The Vera C. Rubin Observatory was constructed on Cerro Pachón in northern Chile, at an elevation of roughly 2,700 meters. Its location was carefully selected because the surrounding environment provides exceptionally dark and dry conditions for astronomical observations. The nearby Atacama Desert is among the driest places on Earth. Clouds are uncommon, rainfall is extremely limited, and artificial light is almost non-existent. Those conditions allow astronomers to observe the night sky with remarkable clarity. The observatory carries the name of Vera Rubin, the astronomer whose work provided some of the strongest observational evidence for dark matter. During the 20th century, Rubin studied the rotation of galaxies. According to the amount of visible matter inside those galaxies, stars farther from the center should have been moving more slowly. Instead, observations showed something very different. Stars near the outer edges of galaxies were moving far faster than expected. The simplest explanation was that galaxies contained much more mass than could be seen directly. Something invisible appeared to be providing additional gravity and preventing these galaxies from flying apart. That invisible component became known as dark matter. Rubin's work helped transform dark matter from a theoretical possibility into one of the central questions of modern cosmology. The observatory itself began as a much smaller concept. During the early planning stages, scientists imagined a telescope that could investigate dark matter. Over time, that idea expanded dramatically. By the beginning of the 2000s, the project had evolved into what was then called the Large Synoptic Survey Telescope. Its mission was no longer limited to dark matter. The goal became much larger: create a comprehensive, repeatedly updated survey of the night sky. The project eventually received support from major U.S. scientific institutions and private contributors. Construction, engineering, and testing continued for many years until the enormous telescope finally became operational. At the heart of the observatory is the Simonyi Survey Telescope. Its optical system is unusual because it uses 3 mirrors rather than the 2 mirror arrangements common in many large telescopes. This design allows it to produce sharp images across an exceptionally wide field of view. The telescope can photograph roughly 9.6 square degrees of sky in one exposure. Put another way, an individual image covers an area more than 40 times larger than the apparent surface area of the full moon. Its primary mirror is about 8.4 meters across. But the mirror is only part of what makes Rubin remarkable. Behind the optical system sits the LSST camera, one of the largest astronomical digital cameras ever constructed. The instrument weighs several tons and contains dozens of highly specialized sensors. The camera can observe the sky across 6 different wavelength bands, extending from ultraviolet adjacent wavelengths through visible light and into the near-infrared. Its filter system can rapidly change between different wavelength ranges, allowing scientists to gather different types of information from the same region of space. This means that Rubin does not simply produce pretty pictures. Each image contains scientific information about the brightness, color, position, movement, and changing behavior of astronomical objects. The combination of a huge mirror, enormous field of view, rapid movement, and a massive camera gives Rubin an unprecedented ability to survey large portions of the sky. When the first images were finally released, astronomers around the world had been waiting for years to see what the telescope could actually accomplish. The observatory's first public images arrived in June 2025. The initial observations were essentially a test of the system rather than the full 10-year survey. Yet even during this early period, Rubin detected an astonishing number of astronomers. If something suddenly becomes brighter, disappears, moves, or appears where nothing was previously visible, computer systems can recognize the change. This is where Rubin becomes especially powerful. A supernova that might previously have been discovered only after it had already begun fading could potentially be identified much closer to the moment it explodes. A variable star could be monitored throughout its changing cycle. An asteroid could be tracked across multiple observations. And an unusual object entering the solar system could potentially be detected earlier in its journey. The amount of information involved is enormous. Rubin is expected to produce tens of terabytes of data every night. That information will be transmitted from Chile to processing facilities in the United States, where automated systems will calibrate the observations, compensate for atmospheric effects, identify moving objects, and search for transient events. Scientists will not need to inspect every image manually. Instead, computer systems will identify the observations most likely to contain something interesting and distribute alerts to researchers. By the end of the 10-year survey, the observatory is expected to have catalogued tens of billions of astronomical objects. The final archive could reach hundreds of petabytes. That scale of information would be difficult to imagine using traditional astronomical methods. But Rubin is not simply designed to discover more objects. It is also designed to help answer some of the biggest questions in physics. One of those questions concerns dark matter. The material we can directly observe makes up only a small fraction of the universe's total mass-energy content. Dark matter appears to account for a much larger portion, even though it does not emit or reflect light in the way ordinary matter does. Astronomers know about its presence primarily through gravity. For example, galaxies rotate in ways that cannot be explained by their visible stars, gas, and dust alone. If only visible matter existed, stars near the outer edges of many galaxies should orbit more slowly than they actually do. Instead, their rotation speeds remain surprisingly high. This suggests that enormous halos of invisible matter surround galaxies. Rubin will help scientists study this invisible structure indirectly. One method involves gravitational lensing. When massive concentrations of matter lie between Earth and distant galaxies, their gravity can slightly distort the light traveling toward us. By measuring those distortions across enormous numbers of galaxies, astronomers can create maps showing where mass is distributed. Because dark matter contributes to that gravitational effect, Rubin's observations will help scientists reconstruct its distribution across large portions of the universe. Another major mystery is dark energy. Observations show that the expansion of the universe is accelerating. Scientists use the term dark energy to describe whatever is responsible for that acceleration, but its true nature remains unknown. Rubin will investigate this problem by studying the changing structure of the universe across cosmic time. It will observe enormous numbers of galaxies and supernovae and measure how large-scale structures have evolved. Scientists want to determine whether dark energy behaves like a constant property of space or whether its influence changes over time. If dark energy turns out to behave differently from current expectations, the consequences could be profound. It could force scientists to reconsider some of the fundamental assumptions behind modern cosmology. Rubin is also expected to become an extraordinarily powerful asteroid detector. During its early observations, the telescope identified thousands of previously unknown asteroids in only a short period. Among them were several objects classified as near-Earth objects. These are asteroids whose orbits bring them relatively close to Earth's orbital neighborhood and therefore deserve careful monitoring. Finding potentially hazardous objects earlier is extremely important. An asteroid detected many years before a possible close approach provides scientists with far more time to calculate its orbit and evaluate possible responses. The observatory's repeated scanning strategy is particularly useful for this purpose because moving objects can be identified by comparing images taken at different times. Rubin will also have a special role in searching for visitors from outside our solar system. Astronomers have already discovered a small number of objects that appear to have originated beyond the solar system. The first confirmed interstellar object was discovered in 2017. Its unusual shape and motion generated intense scientific interest. A second interstellar object was discovered 2 years later. Unlike the first, it behaved more like a conventional comet. Both discoveries were difficult to study because astronomers found them relatively late in their journeys through the solar system. Rubin's wide field of view and rapid survey schedule could change that. If another interstellar object enters our solar system, the observatory may detect it much earlier, potentially providing researchers with a significantly longer period in which to observe it. Scientists expect the full survey could reveal many more such visitors. Each one would represent a rare sample of material formed around another star. That means these objects could provide